All right, so let's take a look at this first question. Open top cylindrical drum. So again, little silly things like making sure you're careful about the fact that it's open top and not including the top portion. Okay, when you've got a question like this, one thing you might even want to do before you start is take a look at the units, kind of make sure that everything is matching. And in this case here, the volume's given in meters cubed, the area is given in meters squared, so you don't have to worry about doing any kind of changing of units. Okay, so again, even though this is a fairly straightforward one, I always start with a diagram, and here I started with my given, the fact that I know that the volume, which is pi r squared h, is given by that. Okay, and then what I do is I try to create my model. So in this case here, it wasn't just about minimizing the amount of, I guess, cardboard or whatever it is we're using to create this. I guess it wouldn't be cardboard, maybe some kind of metal. It's actually the cost, not just the amount of material. Okay, and so clearly it's not just about minimizing the amount of material, because they don't always cost the same. So I know that I've got the base, pi r squared. Okay, that's the area, and this is the cost per given area. And then I add the same thing, $500 times the area of the side, which just represents the lateral area. Okay. Now, of course, this has two variables, and this is where now I used the constraint that the volume had to be equal to 5, and that allowed me to write one variable into terms of the other. Now, of course, I chose to write h in terms of r squared, because here, if I isolate r, I get one nice one, because r squared, I won't have to take any square roots, but I'm going to end up with a square root. If you did do it the other way, you should get it. You should be able to get the answer just as well. It's just not going to be nearly as nice. All right. So by the way, don't forget to just stop me if you have any questions. So I just input that in. Okay. And I simplify, and here's my model in terms of one variable. Now, something that's very important that's going to come up in number 3 is when I ask you for a model, it's not enough to just give me the equation that you're going to use. You also have to give me the domain. Now, in this case here, there wasn't too much to this domain, because there's no restrictions on, one variable needing to have, like there was a homework question where, the height had to be only so large, or none of the dimensions could be less than 5 centimeters. So this might be a little more complex if you're given some kind of constraint, and here they really didn't. Okay, a more realistic version of this problem would have probably put some constraints on those variables. Okay, so model includes equation and domain. So take note of that if you didn't do it in number 3. Okay, and then from here, I just take my derivative, I solve for 0. Okay, there's only one critical point. Okay, but because I'm not working with a closed interval, I have to justify that this value here indeed gives me an absolute minimum and not just a local minimum. So it's definitely a local minimum. But here I see that to the left of 1.38, the function is always decreasing, and then beyond that, it's always increasing. So it's can never come back down. Okay, and so this means that this does represent a minimum value. And here we got to go back to what they're looking for. And since they're looking for the dimensions, I've already found the radius, and now I have the height that I can calculate from this relationship here. All right. So any questions here as to this problem? This is a pretty standard. This is about as standard an optimization problem as you can get. Excuse me. Again, it's just about being careful and make sure you're justifying everything you need to justify. Okay. So I do see someone came on with the name iPhone. So remember what I said, you need to have your name. So let me see how to, Okay, so unfortunately, I'm going to have to remove iPhone. You can just come on with a different name. Okay, just make sure everybody else has their regular name. Yeah. Okay, so any questions here? Nope. All right, so let's move on to number 2. And number 2 here asks us to determine all points where the relation defined by this equation here has a horizontal tangent. Okay, so in the end, we're still looking for the same thing. Sorry, let's see. Samia, one question. You had to justify the critical point, otherwise you'd lose marks. Oh yeah, certainly. Okay, because here, who's to say that, first of all, this doesn't even, maybe this actually gives you an absolute maximum. I don't know any of that. Okay, you have to assume that your grader needs to see all the information. So it's not like I'm asking you for a lot, but yeah, definitely you would lose marks. In this case here, yeah, you'd have a problem because there wouldn't be one particular solution. Okay. Yep, we post this later on. All right, does that answer your question? Okay, great. So here, we're looking to see where this relation has a horizontal tangent, but you have to think that, you know, even if you have something that's a relation instead of a function, okay, you're still looking for a horizontal tangent, okay, which still means that the slope of this line is equal to 0, okay? And the slope of the line still represents what it always represents, okay? How the y's change with respect to x. So if you're looking for this horizontal tangent, it still has a slope of 0, and the slope is still represented by the derivative of y with respect to x, okay? So you're still trying to determine where the derivative of y with respect to x, in other words, when the change in y with respect to a change in x is equal to 0. Okay. Problem is that we can't isolate y, so this is where we use implicit differentiation. Okay. So here I think I have it in 2 columns. All right. So I just take the derivative with respect to x of both sides. All right. And I apply my derivative rules. Okay, so you'll notice here that when I want to show a derivative of a whole big expression, I'll use Leibniz notation, but then I switch to prime notation just because it means a little less writing to do. Okay, so this is an easy derivative to take because it's with respect to x, whereas here I need to apply the chain rule. Okay, so I think of y as being my u, so the derivative of u cubed is 3u squared, and then times the derivative of u. And again, remember, this represents the derivative with respect to x. This you just have the derivative of y with respect to x. Oh, that's funny. Okay, thank you very much. See, I told you all the mistakes are usually silly mistakes. So let's see if I can fix this as I go along. Okay, so this is gonna be 3, this is just gonna be 2x. Well, that's pretty funny. Good catch on that. I'm glad you caught that early on. So that's just gonna be 2x. Okay, so I'm going to do the same thing. I'm going to collect all the y primes to one side. Okay, except this is going to be, no, that actually doesn't change, 3x squared. This, though, of course, when I bring to the other side, will just be 2x. Okay. Oh, 3y squared. Thank you. Okay, so again, just to confirm what I did, so I just bring together all the terms with y prime, anything that doesn't have y prime to the other side. Okay, I'm going to factor out the y prime here. Let's clean that up. And then now I can isolate for y prime. Okay, and
Tony, the
yep,
2x negative.
negative 2x. Well, this is turning out to be a bit of a disaster. That's okay. We'll take it as it goes. Thank you. See, I actually find this way harder. Yeah, I know. I find this way harder than teaching in a classroom. Besides the fact that it's killing my knees. All right. It's okay, folks. We laugh this off. It's not a big deal. Okay, life lessons here. All right. Before I move on, let me check that this all works out. Yes.
Also, the denominator is still 3x squared. It should be 3y squared.
Oh God, what in the world? Haha. This is 3y squared, 3y squared. I guess I did this a little too quickly. Okay, folks, let's have a laugh. Okay, let me ask you, did I finally get this right? Looks like it looks good. All right, very good. And so, well, now apparently I got to fix this whole thing here. There we go. So negative 2x over, see, I should have just done this on the spot instead of pre-doing it. There we go. So in the end, I want to know when this is equal to 0. And this is pretty funny that in the end, all these mistakes are not going to affect what my next line is going to be, it looks like, because in the end, in order for this to be equal to 0, I just need the numerator to be equal to 0. And so x is equal to 0. All right, so this may affect some of what I do later on because of the squared, but let's see what happens here. Now, are we done? Who wants to tell me why we're not done? No. Yeah, because it says, and again, make sure you look for that bolded and italicized, it is looking for the points, you know? So in this case here, how do I find the point? Well, I just have to put it back into the equation. And look at that, I got the square right in that one there, okay? So I just input x equals 0, and now I see that I have an equation in y to solve. Now, what mistake do I want to avoid here? What mistake do I definitely want to avoid? Who's going to tell me the big mistake people might make here? Any ideas? Well, that's it. I do not want to divide both sides by y, okay? Because I might end up losing an answer. In fact, you would. What you want to do is bring everything to one side of the equation, and then you see that, in fact, you're going to have 3 possible y values. Had you divided both sides by y, you would have lost this answer, okay? So please be very careful, okay? So in the end, it looks like we have 3 answers to this question. And since somebody brought up the idea of this looking crazy on Desmos, I guess we should really take a look at it, okay? We don't want to lose, and I'll show this solution again, although it will be posted. Okay, so let's get Desmos, and let's see what we have. We have x squared, get that right this time, plus y cubed, oops, equals, and what is it? Equals y. And when we take a look here, we see that makes sense that it's at x equals 0, and we have a horizontal tangent when y is -1, when y is 0, and y is equal to 1, okay? So let's close this off. Ugly, oh no, this is beautiful. I guess beauty's in the eye of the beholder or something like that. All right.
Tony?
Yes.
I have a question. Is it possible to solve this by moving all of the values to one side? So if you said 0 equals x squared plus y cubed plus minus y?
Yeah, I mean, in the end, you'll end up having the same thing because you're going to only want to keep anything with y prime on the left and bring everything else to the right. So in the end, it'll just all work out. Okay, you would get exactly the same thing. Okay, it doesn't really help to do that. Okay, so Again, if you could manage silly mistakes, not making silly mistakes like writing it down wrong or replacing X's with Y's, you know, very often these implicit differentiation questions can actually be fairly straightforward, easy questions, and that'll come into play with what I'm going to talk about later on. Okay, any other questions here? I think I finally got the right answer after all that. Any questions? Okay. So let's move on to number 3, where I specifically asked you not to solve the problems, but just to give a model. Okay. All right. So here, this is one of these examples where you have. Let me just switch this around so we don't see the. Okay, where we have number of units, and as we increase the price or decrease the price, the number that we sell, or in this case here, rent out, changes. All right. So here, one thing you notice, it says a landlord manages 100 apartments in a complex. So this is where you have to be careful, because you know that your answer cannot be greater than 100. Okay, so that's going to be one of the constraints on your variable, is that you don't want your, you can't have your number of apartments, and I'm going to make X be the number of units, be over 100. And of course, you can't rent out less than 0 apartments. So right off the bat, I can see that my, domain should be from 0 to 100 inclusive. All right. So now here, what I do, and how you solve it could be different. Okay. So I'm going to solve it by letting X be the number of units. I know some people will probably have solved it where X is the number of price increases. I just kind of insist on doing it this way, just because it's the more standard way of solving these problems. So I just want to introduce you to that. And the idea is to find the price function. Okay, now remember what the price function is. Okay, this represents the price, so the cost of the unit with respect to the number of units being sold, or in this case here, being rented out. Okay, so the X value is the number of units and the Y value is the price. And what they tell us is that when I increase the price by $15, the number of units goes down by 1. Okay. So here, the first thing that it seems to be implied, okay, that this is a linear function, because they say every time I increase by $15, 1 less apartment. So that means I can represent price with a linear function. So I just find the slope, find the B value. Of course, you can also use point slope form if you like. And in the end, I end up with an equation for the price of the unit with respect to the number of units being rented out. Okay, so before I move on, I'll just take a look at this question. How are we supposed to tell what is the X and what is the Y in this sort of scenario? Well, here we know what we want the Y to be, because what is it we're trying to optimize? It says we want to know how much the landlord should charge to have the greatest profit. So our Y value is going to be profit. And in this scenario, I've chosen my X value to be the number of units. Okay. If you choose your X value to be the number of price increases, you're going to have a different equation. Okay. And in fact, if I can find it, I think I did it somewhere here. I'll show that to you afterwards in case you did the other method. All right. So we know that profit is revenue minus cost. So the first thing I do is I calculate this is my revenue function, okay, which is just the number of units times the price of the units. Okay, that's how much money I make, is how many do I rent and how much am I renting them for. And then the cost, well, it says on average, each rented apartment needs $60 invested in maintenance each month. That means that for every unit that I have, I'm paying $60 in costs for that unit. And so now I have my revenue, I have my cost, and I just have to subtract them, okay, to get my profit. So revenue minus cost is my profit function, so in terms of one variable. And what are the constraints on the variable? Well, I can't rent less than 0 apartments, and I can't rent more than 100 apartments, because that's all there is in the complex, okay? And then from there, this is a fairly easy function to optimize if you needed to actually solve the problem, all right? So any questions based on this formulation of the model? And of course here, before I just answer that question, you know, I know this looks like it takes a little more time, but again, it's just expressing all these things in the more natural form. Yeah, so somebody had a question.
Tony, I have a couple of questions.
Yeah.
First one is, in this case, you decided to do like number of houses, or what is it, apartments here?
Yeah.
Being rented. Can I do it like, because the way I did it is did it individual, like dollar increases to the price?
Yeah,
Or
I'm
is
going
it
to
going
show
too
that
far?
one in a second. Yeah, it's 100% correct. There's absolutely no issue with doing it that way, as long as it's done correctly. Now, I will just make, there's, you know, there's a little bit of a issue that comes up using that method. So it's not an issue, but a mistake that's often made. So I'll talk about that in a second. Okay, so in this case here, when we're talking about just the model itself, you don't actually have to take the derivative, okay? Because this is the function that's modeling the measure that you're trying to optimize, okay? Taking the derivative is just part of the process of determining that optimal value. But the model itself just includes the function in terms of one variable. So it's not a valid model until you've written it in terms of one variable and the domain over which you're working, okay? So now real quickly here,
Wait, sorry, Tony.
yep.
So in that case, for 3B, where we're using like the distance formula, in that case, you would still have to give the derivative, wouldn't you? For when we say the model, or just the formula would have been enough?
No, just the formula would have been enough. Again, what's the equation that you're going to use to solve the problem? You don't need to actually find the equation. Sorry, the derivative. Okay. And unfortunately, I can't find that sheet that's got, I'd written it out somewhere. So let me just do it here. Now, the other option here, then this is the one you likely would have seen back in grade 11, is to say, let X be the number of price increases, okay? Okay, and so here, you know, if you're trying to determine your revenue, well, your revenue is still going to be the price times the number of units, okay? But here, the price, you say, well, wait a minute, it starts off at 800, and then I'm adding $15, and then I'm adding $15, and then I could add another $15. In other words, depending on the number of times I add $15, the price for my unit can be written as 800 plus 15x. And then the number of units, well, what happens every time I increase by $15? The number of units goes down by 1. So that would be 100 minus x, okay? This is where you have to be careful. Who can tell me why this is wrong? And this is a very, very common mistake.
Because your X doesn't represent the number of apartments that are being rented.
Exactly. What should be here? What is it that represents the number of apartments that are being rented?
100 minus x.
There you go. And that's, you know, very common mistake when people are doing this question quickly and they accidentally, okay, just use x in the cost equation, okay? Now, where this starts to become a little more dicey is when your cost function is something more complex than just, you know, 60 times this binomial. If it's a much, if it's like a cubic, and then you got to put this into a cubic equation, or if it's an exponential function, got to put that in. It's much more annoying than just using x. Okay. So I just want to take Enoch's question is, can you do 740 as the start price?
Because you know you'll be paying $60 for each apartment anyway.
Oh, okay. I guess, yeah, you can. In the end, that'll, yeah, that should, I think that should work out. 740 plus 15x. Yeah, I think that should work out. I think that works. I mean, check it out. Did you get the same answer?
Yeah.
Yeah, I can't see why that wouldn't work out. Okay. And by the way, when you're doing these questions in the homework, let's say you just, you're starting to get a little tired, you've done a few too many of these, nothing stops you from just finding the model and then using Desmos to check your answer. And if your answer matches the one in the back of the book, means your model was correct, okay? If you don't go through the process of taking the derivative, all right? Now again, we look at part B and we see, well, another type of question that we've seen many, many times is you've got, a parabola or some function, and you want to determine which point on this parabola or points is closest to a given point, in this case here, 1, 0. So in this case, it looks like there's only one answer, but you'll let the algebra take care of that. And the idea here is you find the distance between them using your distance formula. So you have one point, you need your second point. And this is where you do a very important substitution, that because this second point has to lie on the parabola, instead of using y, you replace that by the equation of the function, okay? And so from there, you can now write one of two possible models, okay? Is you can use Pythagoras, okay, and leave this d as squared, okay? Or you can solve for d and use the traditional distance formula and take the derivative using traditional differentiation, whereas here you would be using implicit differentiation. And I see here that I see that here there's no restriction on what x can be equal to, so that's why the domain is just x, an element of R. Okay. So now here, there's a question, is it necessary to find the x-intercepts of the parabola? No, but I figured since this factored easily, yeah, I was able to draw a nicer diagram. In the end, your diagram is only a guide to how you're going to solve the problem, okay? If it turns out that this, point was sort of inside sort of the parabola, so something like that, and you had two answers, well, the algebra would bring you there. Okay, so I just did it because it happened to be easy to factor. If it was not easy to factor, there's no way I would have used the quadratic formula to draw my diagram. Okay, so not necessary, but I did it because it happened to be easy. Okay. So here it says, wouldn't you know that the point won't be to the other side of the vertex, so the domain could be smaller? Yeah, I could, but there's no kind of need to do that. I think there might have been a question where I might have limited. I think it was something that looked like this, where, I kind of knew there was no way my points could be below the x-axis, so I just limited the domain. But again, it, the algebra would have taken me there anyways, okay? Any other questions on this one here? Okay. No, not necessarily, because it could be, I mean, again, it could have been that, remember, this parabola is could have been that the point was somewhere over here, in which you'd have a negative x value. Okay, so remember what x represents. It represents the x coordinate of a point on this parabola. Okay, so, obviously it wouldn't be the case here, but let's say this parabola, oh, my thing froze. Let's say this was my parabola, and there was my point. Then the point at which was closest to it would have had a negative x value to it. Okay, so there's no need to, I wouldn't put that restriction on the x value. All right, so again, the main thing I wanted to say about these two things here is that when you're giving me a model, it has to include the domain, and you don't have to start the process of optimizing. In other words, you don't actually have to find the derivative. That's not what's being asked for. All right. So let's take a look at this last one here. Okay. And this is maybe the question on this quiz that I would say is a thinking question, okay? Because it's not necessarily as straightforward as some of our other related rates questions. There's a little bit of a twist. So here they tell us that the volume is changing at a rate of 500 centimeters cubed per second, and it's decreasing, okay? And they give it to me at a particular moment in time. And then it asks us to determine the rate of change of the surface area of the cube when its side length is equal to 10. All right. So I'm trying to find the rate of change of the surface area. So I guess it kind of makes sense that the first thing I would start with is the relationship that I have for area. But the relationship I have for area is with respect to side length. Okay. So unfortunately, that's not the information I'm given. So there's two sort of routes you can take here. I'm going to show you one of the routes, and then we'll take a look at another route you could have taken. All right. So here, what I did is I said, you know what, let me just work with the relationship for area that I have. So, area is 6 times x squared. If I call x the side length, I just took the derivative of both sides, and I get to this point here. Okay, so notice here I had to apply the chain rule. So first I had to take the derivative of 6x squared, which is 12x, and then times the derivative of x with respect to t. Okay. Now, at this point, I realize, oh, wait a minute, I have the x value because it tells me when the side length is equal to 10, but I don't have the rate of change of the side length. So this is where I said, well, hey, you know what? Let me use the fact that I know the rate of change of the volume to find this. So what I did is I set up, okay, I set up another related rates equation, this time with the volume. So I took my volume equation, took the derivative with respect to both sides, okay? And now I have enough information to calculate the rate of change of the side length because I know the volume's changing. Again, it's decreasing at a rate of 500 centimeters cubed per second, so negative 500. I have the x value, so I was able to calculate the rate of change of the side length. And now I was able to input this back into the equation for area, okay? So now I found the rate of change for the side length. I have the specific side length for which I'm determining rate of change of area, and there you go. I end up with my final answer, okay? Now notice here, I can give my answer in two ways. I could give it saying the rate of change is negative 200 centimeters squared per second. This implies that it's decreasing, or I can describe it and say the area is decreasing at a rate of 200 centimeters squared per second, okay? So I guess this is the more sort of layman's version of how I would describe this behavior. This is maybe the more mathematical description for it, okay? So here, again, like I said, bit of a thinking question because you can't determine it directly from the area relationship that you know. You had to use the volume relationship to find the rate of change of x, and then use that to find the rate of change of a, okay? Now, did anybody solve it another way? Because I would say that there's another way of doing it. It's going to involve maybe some stuff that's not quite as nice. Did anybody have any other, did anybody try anything else here? Oh, that's yeah, that works. I see what somebody did here is they said, well, I have a is equal to 6x squared, and yeah, v is equal to x cubed. And so what they did is they said, well, wait a minute, if I divide both sides by x, actually that's clever. I don't think I've ever seen anybody try that one, equal to x squared. And so now I can just replace x squared by v over x, okay? And now what do I have? I have a relationship between the area and the volume directly. Now, of course, what am I going to have to use when taking this derivative? I got to be careful. Okay. You're going to have to use the quotient rule. So that's a little bit annoying. Okay. Any other suggestions as to what we could do here? It's sort of similar. Okay. Well, the other thing you could have done is isolate. Oh, yeah. Go ahead.
I just isolated from x for x in the volume equation.
There you go. The other way to do it is to do a substitution, is to isolate for x, which is equal to the cube root of v, and then put that into the equation. So area is equal to 6 times the cube root of v squared, okay? Which in the end is not so bad, because I can just write this as 2/3, and now I can differentiate both sides, okay? A prime is just equal to 6 times 2/3, v to the negative 1/3 times v prime, okay? And of course, the annoying thing here is I have to deal with these roots, okay? But I know what v prime is, and how can you calculate v at that specific moment? Well,
you don't actually have to deal with the root, because it's just going to be like when you calculate it, it's just going to be x to the power of -1, right? Because it's the cube, right? The cube root of v. So it's
there you go. Yeah, that makes sense. That here 6 times here. I'll just keep this all together. That this is going to be v prime over cube root of v, and cube root of v is just equal to x. Okay, and then you have that information. So 3 different ways to approach this problem. Okay, so just to show you that sometimes you might take a slightly different turn. There's a way to solve it, as long as you're using you're avoiding those silly mistakes that I was making in number 2. Okay, so just to give you a sense here, I would say for this quiz, number 1, very straight ahead application question, nothing too fancy here. Same thing here, kind of straight ahead application question. These, again, whether I ask you for just the model or to solve them, because we've seen these types of questions before, I would say these are application questions. This one here, because there was a little bit of a twist, I would call this a thinking question. All right. So are there any last minute questions on the quiz itself before I move on to other things? No? Okay.
Tony.
Oh, yep.
How much time would you expect us to take on this quiz of this size?
Let's see. I should have counted. I figured an hour is more than enough. I didn't actually think about it. So I would say this is maybe, 8 to 10 minutes for this one here. Maybe 8 minutes for that one there. So let's say 18. To come up with the model, maybe 6. So it's 24. Maybe 5, 29. Maybe, 35, 40 minutes. 40 minutes is probably what I'd give. Okay. Anything else? Okay, so again, before I stop recording, I do apologize for all those that onslaught of errors for number 2. Okay, so I'm just going to turn off the